Hi, my name is Serge, and in this presentation, I'll be sharing my final project where I explore using diffusion models, not to just generate images, but to classify satellite vehicles without any retraining. So why this topic? I got interested in this because diffusion models are, they're the cutting edge of generative AI. At the same time, labeling satellite imagery, especially for rare or military vehicles, it's difficult or expensive. So I started wondering, could we flip it a little bit and use a generative model like Stable Diffusion to classify vehicles in satellite images purely based on prompts. So what is a diffusion model? At a high level, a diffusion model, takes noise and slowly transforms it into a clear image. They're trained to reverse the noise process one step at a time. So today's models like Stable Diffusion, they do this in a compressed form called latent space, which makes things more scalable and much faster to compute. Zero shot, it means the model can label something it's never seen in training just by comparing it to a description. Normally this is done using embeddings like in clip, where the model checks which prompt is closest to the image. But with diffusion, you're instead asking, which prompt helps the model best denoise this image. The one with the lowest error is likely the best match. And the concept here comes from a 2023 paper called Your Diffusion Model is Secretly a Zero-Shot Classifier. In there they showed that you can treat denoising error as a similarity score. If a prompt helps the model denoise more accurately, it's probably the right class. So in my case, I didn't generate images. I did the reverse. I took actual satellite crops and asked Stable Diffusion, does this look like a pickup truck, a bus, et cetera, et cetera. For each prompt, I checked how well the model predicted noise, and whichever had the lowest error became the predicted class. This diagram shows how that process works visually, from image encoding to noise prediction and finally classification. And now I'll walk you through the notebook and show how these two ideas, diffusion and zero-shot classification, come together. So before jumping into satellite imagery, I wanted to sanity check the general idea that denoising behavior could be useful for classification. So I started with CFAR 10. It's a balanced, simple data set with 10 common classes like airplane, truck, and ship. More importantly, it's the data set that the DDPM model I used was trained on. So here I load the CFAR 10, test set using torch vision. The data set, over here, I normalize the images and load them one at a time so I can test them individually. And next I wrote a quick function to visualize, a few sample images, just to confirm everything loaded correctly. Then I loaded the model from Hugging Face. Now, one thing to note: this model, the DDPM model, isn't like Stable Diffusion. It doesn't use prompts. The class conditioning is baked into the model. So when I loop over the class names here, I'm not actually giving it a text prompt. I'm just measuring the denoising error as is, unconditioned across each class. This still lets me check if I give the model a noisy version of the image, how well it can recover the original, under each class's generative distribution. The one with the lowest error is treated as the prediction essentially, and we kind of see that over here. Original was ship, and the predicted one was ship with the lowest errors. Yeah, so all right, over here, now we can kind of go through how I actually combined all of this inside this notebook, for the satellite imagery. The XView dataset, it's delivered as a GeoJSON format. It's a geospatial file that contains annotations, for thousands of objects, detected in satellite imagery. So each entry includes, a type ID for the object classes, an image ID, and a bounding box defined, in pixel coordinates. So the first thing I did was parse each object and extract its image ID, class, and bounding box. I wrapped this into a data frame for easier filtering. Now the raw type ID values go from 11 to 94, something like that. But not all of those are valid. So I use the mapping from Ultralytics, to convert them into class indices from 0 to 59. That way I can consistently map each vehicle type to its known label. From there, I filtered down the data set to just like 40 vehicles, vehicle classes that I really care about. Things like small car, dump trucks, sailboats, and I remapped them to new IDs, starting from 0, to keep everything tidy. So over here, it's a little interesting. We can see that the class distribution, it's extremely skewed to one class, small car. It makes up the majority of the data set. It could be a big problem for classification because, rare classes like dump truck or, helicopter, barely show up. So I plotted out the class counts just to visualize the imbalance. And right over here, we can see an example of the raw satellite images, what they look like. To actually classify these vehicles, we need to isolate each one. So I took the bounding boxes from the annotations and cropped them from the original satellite images and added padding to make sure the model could see a little context, like shadows or nearby objects, and sanitized the file name to avoid any kind of saving issues. I also filtered out any bad crops, like ones that were too small or where the bounding box wasn't valid. Then I saved everything into a new folder of clean vehicle crops, and and here's some examples of of the images. So now that I had the crops, I needed to figure out how to talk to the model about what's in each image. So since Stable Diffusion was trained with text image pairs, the prompts matter a lot. So I created a prompt for each vehicle class, using natural language phrasing like satellite image of a small car. This way the model had some context from the prompt, even though it wasn't trained specifically on satellite images. I saved all of these prompts into a CSV with 3 columns, class index, class name, and the prompt itself. This CSV basically became the bridge between the numerical predictions and the natural language descriptions. The model needs to make sense of the images. It was essentially critical because the classifier logic depended or depends entirely on how well the prompt matches the visual patterns in the image crop. So if the prompt is vague or off, the error score will be worse. So, and then the natural language prompts, become the labels. I'm not training a model to learn those, just checking which one produces the lowest denoising error. Um, Now I load the core components of Stable Diffusion. This version runs in latent space, which is, it's important because it makes inference way faster, and it still keeps the important visual details. I'm using Euler schedule and casting everything to float 16 to save on memory. Um, Graphing. Or I'm sorry, grabbing the VAE tokenizer, text encoder, and the UNet directly from the pipeline. And these are the pieces we need for our zero-shot setup. The tokenizer and the encoder, they turn the text prompts into embeddings, and the UNet, it handles the denoising. So if you look at the text encoder here, it's a full clip text model with a deep transformer stack. So even though we're not training it, there's a lot of structure behind how these prompts get understood. Next, I tokenize the prompts where the prompts that we created earlier, and one for each vehicle class, like satellite image of a dump truck. And these get padded and converted into embeddings using clip text encoder, and we use these later during classification. Now, for the images, I pre-process each crop and encode it into latent space using VAE. Stable Diffusion doesn't denoise raw pixels, so it denoises in this compressed space, and that's kind of like where the magic happens, right? The VAE transformers are 384 by 384 crop into a smaller latent representation that we can work with efficiently. This step also, it filters out noise and sharpens the relevant features, which help with semantic matching during classification. Now here is where everything kind of comes together. I define two functions. In eval error, I simulate the diffusion process. I take the latent and random Gaussian noise and run it through the UNet for each prompt. Then I compute how far off the predicted noise is from the true noise, and that difference measured using like mean squared error is our confidence score. The second function, it handles which time steps and prompts to evaluate. It starts with a bunch of possible class prompts and gradually narrows them down over a few rounds and finally picks the one with the lowest average error. The important thing here is we're not training anything. We're testing the UNet like a frozen, pre-trained generator and using its, denoising error as a similarity metric. So the lower the error, again, the more confident the model is that the prompt matches the image. And what's cool is that the logic is scalable. You can throw 40 prompts or 4,000. It'll keep working the same way. All right, now that the classification logic is working, the next step is to scale it. I've got I went through well, actually no, I've got over 260,000 cropped images from the XV data set, and I wanted to run the zero-shot classification on them, but to make things manageable, I process the images in chunks of 1,000 at a time. Each image goes through the pipeline. I load the crop, encode it into latent space, and run the full denoising error loop for all like the 40 class prompts. So then I store the results in a CSV, including the predicted class, the ground truth, and a dictionary of denoising errors for every class. This way I can analyze everything later on without, having to rerun the expensive inference. The script also, it supports checkpointing here. If I stop or get interrupted, it picks up from where it left off by, skipping images that have already, that have results, saved. This was kind of key processing, where I went through 20,000 samples, but excuse me. So yeah, finally, I'm sort of inserted a short pause between chunks to avoid memory buildup and, keep things kind of stable on the GPU. Yep, so now let's take a look at how the model actually performed on some individual examples. And yep, so what you're seeing here is a mix of both correct and incorrect predictions, from the model. So on the left, we have the crop satellite image. The model was trying to classify, and below that you'll see the ground truth class and the predicted class, along with their respective denoising errors. And on the right, I've plotted the top 5 most likely classes for that image based on the lowest denoising errors. These bars are, helpful for understanding what the model was thinking. So in some cases, like cement mixer getting misclassified as scraper, or small cars being confused with oil tankers, the denoising errors are really close. It suggests the model sees some semantic overlap. It's not just making random guesses. It's actually applying a consistent logic, even though it's not always aligned with the label. And occasionally, it does get things right. Like we'll see, the truck with the box at the bottom here. That shows that when the model's generating, model's generative prior strongly matches the image content, it can correctly identify the class. Yeah, so this kind of visualization gives us, insight into why the model failed, not just, that it failed, which is, super important when you're evaluating these zero-shot models. Yeah, so now let's dig into how the model actually performed, despite, using a, powerful pre-trained model like Stable Diffusion. Was, originally trained on photographic data. The results on satellite vehicle crops weren't great in terms of raw accuracy. We're looking at like 1.15, top 1 accuracy, which is well below what you'd want for any, classifier. Now on the confusion matrix, it's, pretty clear most predictions were clustered in just a few classes, like small car, passenger vehicle, and truck. A lot of the rarer, more specific classes like yacht or crane truck were either never predicted or only got 1 or 2 correct hits here. But yeah, if we look at the classification heat map, you can see that most of the, let me just, but yeah, most of the F1 scores were extremely low, like across the board. The model basically failed at confidently predicting most of the rare or complex classes. Interestingly, small cars, which dominated the data sets in terms of volume, didn't dominate the prediction. In fact, we could see that it had a low low recall, kind of meaning that the model didn't overfit the most common class. It's actually kind of encouraging. It tells us the model isn't just blindly guessing based on frequency. So yeah, in terms of classification performance, it's not good, but it's, well, only half the story. What's more important here is why the model made those choices, and how consistent its internal logic actually was. So now that we've seen the accuracy is pretty low, the next question is, was the model at least being internally consistent? Like, did it make the best guess, or the best guess it could, or if it turned out to be wrong, or even if it turned out to be wrong, right? And essentially, that's what this section is really all about. Um, before we were just looking at whether the model predicted the correct class or not, but now we're kind of digging a little bit deeper. We're comparing the denoising error for the predicted class versus the ground truth, essentially. So here's how I did that. Essentially, for each prediction, I pulled the denoising error for both the predicted class and the actual ground truth class. Then I just subtracted them, and essentially that gave me the error gap between the two, and if the way that I view this gap is positive, that means that the model preferred its predicted class. Um, you know, so essentially it had a lower error. If the gap is negative, then the model actually scored the ground truth class better, but still didn't choose it, and that's a kind of logic fail, right? Now, if we look at the histogram, you can see it's super skewed towards small positive values. And in fact, there were 0 predictions that had negative gaps. That means that out of the 20,000 examples, the model never predicted a class that scored worse than the ground truth. So essentially, what does that tell us, right? So even though the accuracy was bad, the model was very internally consistent, right? It always chose the class that had the lowest denoising error, so its reasoning actually checks out, right? It didn't guess randomly, it just had wrong prior knowledge for this kind of data. All right, so stepping back, did this work? Well, sort of, right? The model didn't do a great job of actually naming the correct classes. Our top one accuracy was just a bit over 1%, but what was impressive is that the model consistently chose the class with the lowest denoising error. So it's not a total failure. It shows that diffusion models can act as semantic scorers, and they have a sense of this image feels most like a pickup truck, or this one matches a yacht, even if they weren't trained to classify satellite vehicles. This whole project shows that zero-shot classification, though denoising error isn't just it's not just a gimmick, it's a real signal, and while the classification layer isn't strong out of the box, the foundation is definitely there. So I guess, let's talk about what held the model back. I mean, first, there's a domain mismatch. Stable Diffusion was trained on web photos, or images, and then not satellite imagery, right? And that's a massive gap. So we're asking it to recognize things it's probably never seen from that angle, scale, or texture. So second, this is a zero-shot setup. There's no learning from labeled examples. We just prompt and look at denoising error. That's flexible and creative, but it also means we're flying essentially blind on things like intra-class variation. And third, the XV data set is very imbalanced. Small car appears over 200,000 times. So it's hard to know, if the model is failing because it's confused or just because there's not enough data. And lastly, the prompts themselves are kind of a bottleneck, saying, a satellite image of, a small truck might help steer the model, but it's still vague and doesn't fully translate to pixel level differences in aerial views. Um, that said, there's a lot of room to push this further. First I try fine tuning to stable diffusion on satellite imagery, either directly on XView or through transfer learning from models like Diffusion Sat, where that were made for this type of data. Second, maybe prompt engineering could go deeper. Instead of one sentence, maybe use multiple variations. Um, to wrap it up, generative models like Stable Diffusion, they weren't built to classify, but with a little bit of creativity, they can. So this experiment shows that even when they're wrong, their reasoning has a little bit of structure, and that opens up a lot of possibilities for future work in you know essentially hard to label domains like satellite imagery. So thank you for listening.